Welcome back. In this lesson, we will discuss about friction on a horizontal surface for which the applied force is inclined at an angle to the horizontal. That is to say, the applied force is not horizontal. If you can remember, in our previous lesson, we talked about friction on a horizontal surface where we have an object of mass m and we have an applied force P that is acting horizontally. And we've said that if this object is to be in limiting equilibrium or in motion, the frictional force have to act in the opposite direction, F. We have two other forces. We have the normal reaction R and we have the weight. Okay? We've said that if this body is at rest, the pulling force or the applied force is equal to the frictional force. And we've said that the normal reaction R is equal to the weight of the object. This is only true when the applied force is exactly horizontal. But in this lesson, we want to discuss about a situation for which the applied force is not horizontal, but instead is inclined. That is, we will have the applied force acting inclined to the horizontal. Okay, so this is the applied force and it makes an angle theta with the horizontal. For a situation like this, it will be wrong to assume that P is equal to F, and it will also be wrong to assume that R is equal to W, because there are other important forces that need to be considered. So if this is the applied force that is acting inclined, we have to resolve this force into horizontal component and vertical component. Let's call the horizontal component of this force as Px. And if we should establish a triangle here, we will have the vertical component of this force P as Py. So we have a triangular shape here and we can use it to do resolution. We have Py, we have P, the applied force, and we have Px. This is the angle theta. So as you can see, we can resolve this inclined force into its vertical component and its horizontal component. Now, using sine theta is equal to opposite all over hypotenuse, we'll have sine theta is equal to the opposite is Py divided by the hypotenuse will be P. Then Py is equal to P sine theta. This force is the vertical component of the force P, or the applied force. And it is the force that tends to lift the object from the surface. Okay? Now, if we use cos theta is equal to adjacent all over hypotenuse, going to the diagram, the adjacent is Px, the hypotenuse is P. Then we will have cos theta is equal to Px all over P. So if I cross multiply, I will have Px is equal to P cos theta. So that is the horizontal component of the applied force P. Because I now know these components, I can go back to the diagram and say Px is equal to P cos theta and Py is equal to P sine theta. Then we can make another resolution here. So because we have two vertical forces, which are the normal reaction R and Py, we can now say R plus Py is now equal to the downward force, which is the weight. Okay, so R plus Py is equal to the weight. So if we have to develop this equation, that will be R plus Py is P sine theta. This is equal to the weight. So this is an important formula in a situation like this. But we know that weight is equal to mass times gravity. So therefore we can say R plus P sine theta is equal to mg. This is also important. So as you can see, for situation like this, R is not directly equal to the weight, but R plus P sine theta is what is equal to the weight. And if this body is in equilibrium, that is, if it is at rest, then we can say that the P cos theta is equal to the frictional force. Okay, so if the body is in limiting equilibrium, F is equal to Px, and that will be F is equal to P cos theta. But we know that F is equal to mu R. That is true for any situation. So we can replace it. We can say mu R is equal to P cos theta. This formula is also important. All right. Now, if we go back to the diagram and we want to establish the relationship when the body is now accelerating. So for this body to accelerate, we know that the P cos theta component of the applied force must be greater than the frictional force. Okay, so for the body to accelerate, the applied force has to be greater than the frictional force. All right, so when the body is accelerating, the P cos theta must be greater than the frictional force. So therefore, we know that the net force will be equal to mass times acceleration. So the net force is P cos theta minus the frictional force. That will be equal to ma. All right. So P cos theta minus the frictional force is mu R. This is equal to ma. We can say by dividing both sides by m, A is equal to P cos theta minus mu R all over m. And you already know how to find R by using R plus P sine theta equals to mg. Okay, so that is all for today. In our next video, we will discuss about the problems and solution regarding friction on a horizontal surface when the applied force is inclined instead of being horizontal. Please do not forget to subscribe, like, and share our videos.